Let's take a look at the first example of recursion. And let's choose some example that should be very familiar to you already, which is about the factorial calculation. Let's revisit the definition for how you can calculate a factorial of certain number, usually positive number. Let's say here, so that's the factorial notation. You simply put an exclamation mark at the end of some number over here. In the case where you want to calculate a 0 factorial, by definition, it's simply just 1. Right? You can right away. You can think about it's a problem that is so small, which you can just know its solution right away. It's more like a base case. But this part over here is not really like a recursive case, because over here you're not really using the factorial of maybe something that's strictly smaller, right? So this is not really recursive definition. But we'll do one exercise together in a moment. If you look at this definition here, it's also rather straightforward. If you want to calculate the factorial of some number that's larger than or equal to 1, in that case, this will be the way to calculate it, right? Let's now take a look very quickly. For example, let's say I want to calculate the factorial of 5. Okay, let's say. So I want to calculate 5 factorial. What would that be? Apparently, 5 over here, it doesn't really match this condition over here, right? It will actually match this condition here, 5 larger than or equal to 1. So it's going to be 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So 5 or 3 to 1, right? That's the multiplication. All right, so that's a 5 factorial. And then how can you actually figure out the recursive solution for n factorial, right? Let me give you a little bit hints, and then you should really try to pause the video and think about it, right? Even though it's such an easy problem, but I would say you really want to practice about how to think recursively, okay? Let me give you a little bit hints. The very idea about solving problems recursively, for example, if you want to solve the problem for 5 factorial, you want to really divide the problem into some strictly smaller problems, right? That's what we want to do. How can I divide the problem of calculating 5 into something strictly smaller? So why don't I divide it into calculating just 4, right? So I'm gonna do some visual hints for you. Look at this part over here. Think about what it is. Is it the solution for some strictly smaller problem for the factorial? And then if you're able to get that strictly smaller problem solution, what else do you need to do in order to combine that to get the solution for the original big problem for 5 factorial? And then knowing that, you should really be able to derive the recursive solution for any general number for n factorial, where n can be arbitrarily large. Right? So that's something I want you to think about. Right? Pause the video and derive the recursive solution for the factorial problem. And for recursive solution, you should get base case and also recursive case. All right, and now pause the video. All right, assuming that you thought about it, so let me follow up with my hints. You can see this part over here, 4 times 3 times 2 times 1. This is exactly the problem for the solution for 4 factorial. And then take a look at the size of the problem. One is about calculating the factorial for 4, and the original problem is about calculating the factorial for 5. So that means you will be able to define the recursive problem. You will be able to define the problem recursively, which this will be simply equal to 5 multiplied by 4 factorial. And to be more precise, it's really about 5 multiplied by 5 minus 1 factorial. Agree? Okay. So you can see this part over here is really a strictly smaller problem. Okay, so this part over here. So this part over here is really a strictly smaller problem size. So what we have done is we try to say 5 factorial recursively is simply equal to the solution to a strictly smaller problem, which is 4 factorial, multiplied by some constant 5. And now, can we actually figure out the recursive solution to n factorial? Right? Definitely we can. Let me just try to visualize that in the same way. I know it's only a simple problem, so maybe should we really go into this many details, I will insist, because I think it's really important for you to see the recursive pattern. Okay, let's do it quickly. So let's say we got n factorial over here, right? By the very definition, it's going to be n multiplied by n minus 1 multiplied by n minus 2 multiplied all the way to, eventually we should really get to minus 2 and then, multiply by 2 and multiply by 1, right? That's the solution pattern. Now, how can we divide it into sub-problems? This part over here, like how we did it before, this part here is really the factorial of some strictly smaller number than n, right? So this part here is just going to be this part here, right? So it's simply just n minus 1 factorial. And this is indeed a strictly smaller problem than n, right? So you can think about, so this case, it will just be equal to n multiplied by n minus 1 factorial. Okay, let me highlight it again. So this part over here is really the strictly smaller problem size. If you compare n minus 1 versus n minus 1 for sure is strictly smaller than n. That's really the essence for solving problems recursively. Okay? Alright, so hopefully you're following this simple reasoning, but it's really fundamental for you to understand how to solve problems recursively. Whenever you're given a new problem, let's say later, right? Every time I will give you a chance to pause the video and think about how to derive the recursive solution. Every time you're given a certain problem over here, you really want to know about how to break it down into strictly smaller problem pieces. That's really the first step. Right? But always I'll give you a little bit hints. But you should really also get natural about how to derive the hints yourself. Let's now go back to the slides. Alright, so that's the recursive solution as we said. And once you get a recursive solution, it will be rather straightforward to really derive the Java code accordingly. Okay, so this will be the Java code over here. Let me just go over that together with you, and then we should really trace it together using some example method invocation. Let's do that. Okay, let's now take a look. So this is the recursive solution over here, right? Let me just highlight again. You can think about n minus 1 over here, compare with the original problem n, right? You can think about to go from here to here. So this is really a strictly smaller problem that we are solving. And not only that, you should also make sure for every recursion, you must have some base case, meaning that you must have the basic units of the problem that can be solved right away. We'll talk about some common error. One of the common error is if you try to define only the recursive case over here, but without the base case. In that case, you're going to write into infinite recursion. That's something we'll see later. Okay, let me just highlight once more. So this part over here is so-called a recursive case. So this part over here is so-called recursive case. Whereas, and this part over here, just this part, right? About something we can solve right away. In that case, 0 factorial, that we know it's simply just 1. We don't need to do any further calculation. And this part over here is so-called the base case. Okay, here, the base case and also recursive case, they're simply just singular. Only a single base case and also a single recursive case. But it's not necessarily like this, always. Sometimes you may have multiple base cases, and sometimes you may have multiple recursive cases. It depends on the nature of the problem. All right, we'll see example later. Okay, so this will be the method, like an accessor, to actually return the factorial of certain number. You can think about this part over here is really calculating factorial of n, right? You can see the n over here, right? You can see the correspondence. We declare some local variable result over here, and then we're going to do some conditional over here. So the conditional here usually is for you to actually distinguish between base case and recursive case. So this part over here will be the base case over here, where n is simply equal to 0. In that case, result should just be 1. Okay. In the case of else is like n is not equal to 0. Okay, and we are assuming that n should be larger than or equal to 0. That's something we assume. Of course, you can also include some exception handling if you like. But for now, let's make that assumption to make things easier to illustrate. So in the else part, so that means n is larger than or equal to 1. In that case, it would be the recursive call, right? You can see here, this is, we're calling the same method factorial. But if you notice the value here, remember we talk about I and j, right? And j must be strictly smaller than I in the earlier illustration over here. If you remember this particular general pattern, right? That one applies just here. Okay. You can see n minus 1 in also n. So we are solving a strictly smaller problem than the original one, right? So let me just highlight it as well. You can see n minus 1 is really a strictly smaller problem. Strictly smaller problem. Okay, it's really important for you to know that. And we are calling the same method over here, so that means this is a recursive call. You can see factorial, the same as factorial over here. And more importantly, you can see we're calling only a single number and also a single integer. So the parameter also match, the parameter type also match. So that means it's really calling the very same method. And this one here is really a recursive call. A recursive call. And eventually we just return the result. And I already made available all the source code to you about all the example we talk about in the lecture. So you can definitely play with the source code and then try to execute different instances of the problem and just to convince yourself. Let's now try to trace the recursive call very quickly, right? Let's see exactly how the factorial 3 will work, okay? And also review how you're supposed to trace method call in the case of how you can trace a method call. In this case, it would be for recursive call. Let's see. What we want to do is we want to trace for factorial number 3, right? So what we're going to do is we're going to actually say here call by value. So let's say we're going to replace this value over here just by n by 3 over here, right? So what we should do is I'm going to say FAC for factorial for short, okay? So factorial 3 should be pushed onto the stack. So now it's currently activated, right? And what's going to happen is we're going to declare integer result over here, but that's fine. And then are we actually going to execute this branch over here? No, because 3 equals 0 is going to be false. So we don't actually execute this branch. Should be quite obvious. And then we go to the else part over here. What's going to happen is it's going to say result is going to be reassigned to n, which is 3, multiplied by factorial of 2, right? It's going to be 3 minus 1. And is factorial 2 a base case? Well, 2 equals 0 is actually false. So it is not a base case. So we cannot solve factorial 2 right away. We cannot. So we still have to go for the recursive case, right? And let me now, for factorial 2, let's now see how we can do it, right? So for factorial 2, let me highlight it. So this is some just another method that we got to push onto the stack. Let me use orange over here. Okay. So what's going to happen is we're going to push to the stack factorial 2 over here. Okay. And factorial 2 is going to call the same method over here, right? So we're going to replace n over here by 2. Think about we are now execute the same method the second time with a different argument value, right? It's going to be 2, which is a strictly smaller problem to solve. And we got 2 here, and then we're going to declare some local variable result, and then 2 equals 0 is going to be false. So we don't really execute the base case branch. And then we're going to execute this part over here. So I'm going to say result is reassigned to, so I'm going to put it here. It's going to be 2 multiplied by factorial of, so 2 minus 1 is going to be 1 over here, right? Hopefully so far you're still following me. And let's now try to highlight this maybe by factorial 1. Let me use pink over here. So factorial 1. And we're going to further suspend. You can see so far we got factorial 3 suspended and we're executing factorial 2. But factorial 2 also involved the execution of factorial 1, which we have to figure out exactly how to calculate it. So that's why this will be suspended and we're going to push factorial 1 into the stack, right? Let's now do that. So we're going to push factorial 1 onto the stack over here. And then we're going to execute this method here for the third time. Specifically, we're going to pass the argument 1 over here for factorial 1. And let's now check. Of course, we declare the result, local variable, and also, are we going to satisfy the base case criterion? The answer is no, because 1 equals 0 is actually false. So we still bypass the branch for the base case. So we're still going to go to the else branch and execute one more time the recursive case. And so what we're going to have is we're going to say 1 multiplied by factorial 1 minus 1, which will be 0. So already here, so that'll be 1 multiplied by factorial 1 minus 1, so which will be 0. Okay, and in order to calculate this, we have to suspend the current factorial 1 calculation. Let me use a different color here. How about purple? Let's say here. So this will be factorial 1 over here. And in order to calculate it, we're going to push that onto the stack. Let's say factorial 0 over here. But it looks promising because 0 indeed will be treated as a base case calculation, which means it will be time for us to return from the stack and keep popping off the element from the stack. We'll see. How do we calculate factorial 0? What's going to happen is we're going to execute this method for the 4th time. And then we're going to use the argument value 0. And then we still declare some local variable result. And then 0 equals 0 is going to be true. So that means we're actually going to execute the base case. So result would just be equal to 1, right? And then in that case, we're going to return the result right away. Okay? And so what's going to happen is we're going to pop it up, right? And then think about what's going to happen is we're going to return. At the same time, we'll return 1 from there. And once we return 1 from factorial 0, we are going to, what will be the next method to execute? It should be the top of the stack, which will be factorial 1. And remember for factorial 1, which I wrote in pink, that one was actually suspended because we were waiting for the result from factorial 0, which is a purple one here. And that one already returned 1. So you can think about that one there simply gave us over here the value of 1 over here. So that means we can now calculate what's the factorial 1. It should be 1 multiplied by the return 1 over here, which will be 1. Okay, let's be very cautious about the color I'm using. I try to be very careful over here. So that'll be equal to 1. So that means we can now return the result for factorial 1. And factorial 1 is simply just 1. So we can, it's now done with its execution. So pop it up from the stack and it's going to return 1 as well. All right, and let's now go further. What would be the next method to actually execute? It will be the next one, the top of the stack, which will be factorial 2. And if you look at factorial 2, this is where we actually got suspended, the point of suspension. Factorial 2 was actually suspended because we were waiting for the result from factorial 1. But now that it's returned, so now we can fill in the result, right? We can use that return result. So this part here is factorial 1, and we know that that one actually returns actually 1, right, from there. So what would be the result for factorial 2? We can now do the calculation. So this will just be equal to 2 times 1, which will be 2. And this result will actually be returned, right? You can see the line over here, right? This result will return. And we can pop it off from the stack, and that one there is going to return 2. And the return value will be passed to the next suspended call in the on the top of the stack. So what will be the next one to execute? We are now moving to almost the end of the execution. The last one to really look at will be factorial 3. And if you recall, factorial 3 over here was suspended because we were waiting for factorial 2 to be calculated. And now that factorial 2 has returned the value 2, so now we can complete the execution. And now for this part here, you can see factorial 2 has returned the value of 2 over here. So that will be actually 2. And what will be the calculation result for 3 times 2, which will be equal to 6. So this will be the ultimate result that's going to be returned from factorial 3 over here, right? So after this, factorial 3 will be removed from the stack, and then it's going to return 6, as we said over here, right? So that's the final result. And that's the correct result because factorial of 3 indeed is actually 6. Let me recap very quickly, but the reason that I really want to do the complete tracing together with you is for you to really see exactly how recursion can be traced. Because if you only look at the recursive call over here, you might be wondering, why would it work if I simply say this is the solution for the n-1 strictly smaller problem, and then simply combine that with some constant here, and then the whole thing will just magically work. As I said before, there is no magic. You really have to see exactly how things will be executed at a runtime using the call stack, right? So using the call stack is one way to trace the code. You definitely should know. There's another way to verify that what you have done is actually correct. Let me show to you, right? Similar to the idea of stack, but just notation is more in some way that's more concise. Okay, let's say we started with the execution of factorial 3. Okay, and for factorial 3, we know that it is actually going to boil down into 3 multiplied by factorial 2, and this part over here is something that's going to be calculated, so factorial 3 will be suspended. So that's why we have to go ahead and calculate factorial 2. Meaning that before we can know the result for factorial 3, we must know the result for factorial 2, which is part of the calculation for this. Okay? And in order to calculate factorial 2, we know that it's going to be 2 times factorial 1 over here. And then for factorial 1, that one there is going to actually be executed, and at the same time, factorial 2 will be suspended. So we're going to calculate factorial 1. And factorial 1 by definition is going to be 1 multiplied by factorial 0. And then in order to calculate factorial 0, we have to suspend factorial 1. And that one there depends on factorial 0. Alright, and because this is actually the base case, so this will just be equal to 1. You can think about this one is going to be returned to this result over here. So that one there is going to be just 1. And then this result over here, 1 multiplied by 1 is going to be 1. And this result 1 is going to be returned back to here. And then factorial 1, we know that it's going to be replaced by just 1. And then when you calculate factorial number 2, 2 times 1 is going to be 2. So 2 is also going to be returned back over here for factorial 2. And so this will be replaced by 2. Finally, if you try to calculate 3 times 2, is going to be 6. Right? So 6 will be the final result for factorial 3. This is a slightly more concise way of tracing the recursive code for simple cases, if you like. But you can definitely experiment with both. You are supposed to know both. All right. I would say the stack trace using a runtime stack is definitely the formal way to go. It's the most precise way to see exactly how things will work. And we're going to trace by using another slightly more complicated example just for one more time. But later on, when I actually talk about other recursive methods, I will tend to use more of this kind of flavor to trace just for simplicity and also conciseness. All right, that's about it. Let's now talk about, before we talk about the next example, I would like to go over some common errors for recursive methods. There are 2 common errors I would like to talk about. Let's now switch back to the paper here. Okay, so the first one, let's consider this alternative definition for the factorial method. We still got n over here, and we say it's simply n multiplied by factorial of n-1. So we still have a recursive call. Is this method correct? If not, why not? All right, pause the video and give me the justification for the answer. Assuming that you thought about it, okay, over here. The reason that this is not good is actually erroneous definition for the factorial implementation is because we actually miss base case. Missing base cases. And what's the consequence of missing the base cases for a recursive method? You're going to resolve in infinite recursion. Let's see exactly how. Infinite recursion. And let's say this. What about we try with, let's say, factorial of 3. Simple one, right? If you try factorial 3 over here, in turn, it is going to make a recursive call on 3 minus 1, which will be factorial 2. In turn, it is going to make another recursive call, which will be factorial of 2 minus 1, which will be factorial 1, which in turn is going to make the third recursive call over here, and that's going to be factorial of 0. In this case, we should have reached the base case already, but there's no base case. That means we're going to make the recursive call for the fourth time, which means we're gonna get into factorial minus 1, and you can see that this will never end. So dot dot dot. So that's why it's going to be an infinite recursion. Depends on the IDE or the execution machine. So for example, in the Eclipse, I believe it will just give you some infinite stack trace, like an infinite stack exception at the runtime, which is not good. Which means your method potentially wouldn't even terminate. There's definitely a no-no you want to do for your recursive method. Even worse, if you are programming in other language like a C, for example, in that case, once you make your program some executable to be executed at a command line, for example, in that case, the infinite recursion is going to eat up all the resources of your computer. So your computer is just going to degrade for its performance severely. So you don't really want to try. Okay. All right. So that's the first common error. What about the second one? The second one is just another alternative implementation for recursion, for factorial. So we still got factorial, we are still making a recursive call, and we do have the base case in this time. We say that when n is equal to 0, we are simply going to return 1. Is this definition acceptable? All right, pause the video and think about it. Assuming that you thought about it, this is still erroneous and will still result in infinite recursion. But why? Well, you want to really, this actually contradicts to our principle, which I spoke about right in the beginning, even before I introduced the example for factorial. You can see here the problem size for the recursive call. Is not strictly smaller. So that's why I emphasize about the phrase about whenever you want to make a recursive call or to assume the solution for a certain subproblem, it must be strictly smaller. So the strictly smaller is really a key to actually make recursion work at a runtime. Let's see why we actually still run into infinite recursion. Let's see. So infinite recursion over here. Okay, let's see why. Let's say we try to do factorial. Let's say factorial of 3. Let's use the same. Factorial of 3. Are we ever going to reach the base case given that it's actually there? The answer is no, because factorial 3 in turn is going to make the recursive call for the first time. But this one here is still going to be factorial of 3 over here, right? And then that one there is also going to make a recursive call, but it's not going to decrease the value for n. It's still going to be factorial of 3, and also factorial of 3, and etc. It will never decrease the problem size, meaning that you can never boil down into the base case. You can never reach there. Okay, so that means you're never able to reach the base case. So if you compare and contrast the two common errors I talk about, in some way they are really about missing the base case. In the first case, there is simply no base case defined over here, even though the problem size is strictly smaller. In the second error here, even though we got a base case over here, but because the recursive call is making a call on the same problem size, meaning that you can never reduce the sub-problem size so that eventually you can go get to the base case. So both are equally bad, I would say, right? If you try either one of them, it's simply going to result in infinite recursion, meaning that your method is never going to terminate. All right, so that's about the two common errors I would like to address, and please keep these two in mind. And then whenever you try to derive the solution for some problem recursively, always remember, number one, you want to have the recursive case, and number one, you want to always have the base cases. And number two, for recursive call, you should always make the recursive call on strictly smaller input size for the problem. Okay. And if you simply just go over them with some more explanation, which I already mentioned, you can also look at the stack trace as well. Okay. And this is actually the tracing for Factorial 5, right? Which is a little bit bigger than the one we did earlier. You can definitely go over that. Okay. All right, let's now take a look at the second example for recursion, which is about the Fibonacci sequence problem.